Hi, Mr. Douglas.
Hi, Walter. How are you?
Good, how are you?
All right. I didn't, I didn't sleep that much last night, though.
Oh, why not?
I was too wired. You were the other guys, too.
Mm-hmm.
Hi, Ryan. Hi, Logan.
Hello. Hello.
Hi, we're all here. All right. Uh, let's get started. I guess the first thing that I need to say is that remind you is that there's no classes next week. Yay. You're looking forward to your week off?
Yeah.
Yes, Logan? Yeah, I bet you are. Are you going anywhere, or are you just hanging around?
We're going to Florida for a little bit,
Oh,
and then
nice.
we'll be coming back. Yeah.
Logan, you gonna be around?
Yeah, same here.
Uh, okay. Let's see. Tests. You guys gonna take the test? Have you taken it yet?
Logan and I took it this morning, and
Yeah.
Okay.
Mr. Year is about to send it, I think.
Okay, great, fine. And Walter?
I took mine yesterday.
Okay. He hasn't sent it yet, or maybe I just haven't seen it. All right, good. Excellent. Let's see. I'm going to start with, well, first of all, I have to make sure for the recording that I share the correct screen. Yeah, which is that one. Okay. And so I'm going to go into Adobe Connect and share my screen. So you guys should go into Adobe Connect.
Okay.
And I'll make you presenters, but not Walter, because I know Walter has trouble. Okay. Walter, I have a question for you.
Hey, Mr. Douglas.
Hi.
I'm about to send you the test
Great.
that Walter took yesterday.
Okay,
I got
super.
distracted yesterday after proctoring it.
Thank you, Simon.
Homework? The physics? Yeah.
Let's see. So I have that, and I'm going to share my screen. Again. This one. Yeah. Close this. Yeah. But I need to get this back. Oh, actually, I don't. I need to get this up. Okay. Can you see that?
Yes.
Yeah.
This is Walter's work. Not what I wanted. Number 6. And then we'll talk about number 7 too. This is the transforming graphs. And I thought it was wrong, but I was wrong. It was right. But I wanted a little more explanation. So Walter, can you go through this for me? For us?
All right. Okay. So it says there's an asymptote at y equals 10, but on y
Right.
equals 2 to the negative x, there's an asymptote at y equals 0, so there's a translation up by 10 units.
Okay.
Yeah. So then I guess we can apply the inverse of that translation to the points 630 and 1215, so we get 620 and 12.5.
Right. I see. Okay,
Yeah,
so
so
then
then,
we have the points. Okay. Ah, all right. So I'm gonna do this. So apply, uh, translate down by 10, right? That's what you mean. Translate the graph down by 10 to get these points. All right. Brian Logan, you with us so far?
Yes. Yes.
Okay. All right, go on.
alright, so then we have 6.6 comma 20 and 12 comma 5.
Right.
And the x coordinate increased by 6, so we should expect that the y coordinate would decrease by 64 times since it's 2 to the negative x, right?
Yeah.
Alright, but then it only decreased by a factor of 4.
Okay.
So
All right. So let me
that
add what
means,
you just
yeah.
said. So, uh, so 2 to the negative x. Let me just copy that. So you would expect this. Uh, yeah. Well, just a second. So the x coordinate. Oh. Uh, 2 to the negative x would decrease by a factor of 64, you said?
Yeah.
Okay. Because that's 2 to the minus 6. Yes. Okay. But y coordinate decreases by a factor of 4. Okay.
So that implies that the x coordinate only changed by 2 in the end. And since um
Oh,
it initially changed by 6, so to get 6 to
okay.
2, it's a horizontal
X
stretch by 3.
coordinate, okay, should change by 2. So that implies horizontal stretch by 3. All right, I'm going to stop there. Ryan Logan,
Uh,
Um,
are you okay with that? Or do you have a question?
I think I'm okay with that. Yeah.
Logan, or do you have a
Uh,
question for Walter?
no, I don't. I was just trying to follow it, but yeah, I think I agree. Yeah.
Okay. All right, go ahead.
alright, okay, so, and then I just plugged in uh, 2 into that, so I got 2 to negative 2 is 1/4. But then we have that we have that the output is 20, right? So then we have to multiply 1/4 by 80 to
Okay.
get 20, so we have
So
that vertical stretch.
1/4 times 80 equals 20. Okay.
So then I just put since it was a horizontal stretch of 3, it becomes 3x, and there was a vertical stretch of 80, and then a translation by 10, so that's 80y plus 10. And then I
Hmm.
just applied the steps, and I got my result.
Okay. Yeah, the rest is pretty straightforward. I put it in. Well, I put it in math tech so we could read it a little better. But yeah, so this is T inverse, and remember that we have to go backwards here. So the last thing being done is adding 10. So the first thing being done is subtracting 10. And then we substituted in y equals 2 to the x. And we get this. And then we solve for y. Okay, that's very good work, Walter. I'm putting this in just to ask you to do a little more in
All
terms of
right, I'll do that.
explaining. Okay?
Yeah.
Okay. Um, 7. Ryan or Logan, were you able to do 7?
I tried.
Okay.
I
Can you-
don't know if it worked out.
Okay. Logan, can you, I'm going to stop sharing my screen and you can share yours and show us what you got. So let me go here. Go back here. Stop sharing. Okay.
I got nothing else.
Wow, that's cool.
Thank you.
Okay.
Wait. Oh, wrong one. This isn't it.
Okay.
Yeah, it's this one.
Okay. Can you make it a little bigger?
Yeah.
Oh, great. Okay.
Uh,
All right. So go up a little bit so we can see the problem. Okay. Okay. So tell us, describe what you did, please.
Well, the natural log function has an asymptote usually at x equals 0.
Mm-hmm.
And that's y and stuff. Oh, I also decided to try and change y equals negative ln of x. I couldn't figure it out with the negative.
Oh, okay. Okay. Fine. Yeah. Okay. Yeah. I mean, I'm not sure that was helpful. So fine. You started with y equals ln x. That's fine.
What did I do here? Oh, it's because I was struggling to find a point where it would intercept at -4 and still have a y-intercept of 8.
Mm-hmm.
So I just this is kind of bad, but I used my calculator and I looked at the natural log, and I found the factor that intercepts at -4 and 8, and it was 7 for my calculator. Like it's somewhere around 7, and so I multiplied 7 by the y value, and yeah.
Okay.
I didn't do it correctly. That's
Well,
what
wait
I'm
a
trying
minute.
to say.
Let's see what you did do. So where does the x minus 6 come from?
The asymptote moved over.
Okay, so you translated 6 to the left, yes?
Yeah.
Okay. Yeah. So the same with you. I want you to say that. Okay. So I needed to translate 6 to the left. Okay. And then I wanted you to tell me a little bit about where the 7y minus 5 comes from, just like you did.
Yeah.
You know, you said it. I'd like you to write a little bit. It's just like Walter.
Okay.
All right, and then the rest is pretty straightforward. Yeah, the rest is fine. And can we check? How would you check this?
I just put it in my calculator.
Oh, okay.
Get the results.
And did it work?
Yeah, it was like 0.3 or 0.2 off, though. I couldn't get the scale factor correct. The
Okay.
7.
All right. Okay. Ryan or Walter, did you have any Anything slightly different? Do you have a different approach or what? I don't want to talk about this too much, but
Pretty much the only thing I got right on that one was the shift in the asymptote. But I now see how to do it.
well, okay. I mean, the 7y minus 5 is not all that clear.
Oh, I got
Walter?
I got an equation that worked.
Okay.
Let's use that.
Did you send it to me?
Yeah, but then I was working on this during the week and I forgot to put an explanation. And I thought I already had it completely finished, so I just have a thing down there.
All right.
But I think I can explain it.
Okay. All right. I'll share my screen and get it up.
Anything close to
I cheated.
I would
sort of just put in my calculator. It's like,
that's fine.
It's not necessarily cheating. I mean, like you said, you got very close, and that's good. Just a little explain what you put in your calculator would have been useful. But otherwise, that's good. That's a good method.
Yeah. Putting in your calculator is just the same as like graphing it with graph paper.
Yeah. Well, I guess so.
Let me get the right thing here. So I'll go up here because I just downloaded it and I didn't do anything else yet. So I just got it. So we'll go to there's March classes, do homework, Walter. This one. Or is it? No. Yeah, 1-1. Okay, it's different. Okay. Walter, what version of Word do you have?
2013.
You do, okay. I was wondering why. So you use DocX, files, right? Rather than Doc, not the old ones. Okay. I'm wondering why you got the rectangles.
I don't know.
I got the rectangles as well.
You got the rectangles as well, okay. I'm not sure why, because when I opened it, there weren't rectangles, so I don't know what's going on. Anyway, okay, here we are, number 7. Go ahead. Tell me a little bit about what you did. Tell us a little bit about what you did. Wow.
Okay. So because the asymptote is at -6, translate it left by 6.
Mm-hmm.
And then it says that the x-intercept is at -4, which yeah, and then like on the original y equals -ln(x), the x-intercept is at -1.
Mm-hmm.
So I guess I was thinking that it seemed to have translated, this x-intercept seemed to have been translated by 3 instead of by 6, so that's why I put the over 2 in the ln function.
Mm-hmm.
And then I just plugged in x equals 0 for the y-intercept, and then I found the scalar multiple that way.
I see. All right.
And it seems to work. So.
Uh-huh. Okay. All right. I think I'll think about this a little more and write something up and send it to you guys. But that's enough for this thing. Not so easy. These aren't so easy. But I guess my point was that let me say this, that I wanted to show you that the method does work for all these things so far. Okay, the next thing, now I want to show you some so this is what I did this morning. The wire. I'm sharing my screen. All right, so I am going to open. I made 2 GeoGebra things, 2 GeoGebra sketches. And one is called Arithmetic on the Number Line. And I got the idea for these from a packet that you can get that, learning GeoGebra, basically. I thought this was kind of cool. And it has to do with complex numbers. You'll see why. All right, now my question is, oh yeah, here are the sliders. Okay, so the idea they gave in the beginning was these are sliders, and how do you add? So just look at the stuff above the number line, not below for now. And how do you add? Well, this is a geometric way of adding. See how this works? Basically adding vectors. So if you go this you learn in first grade, right? You should learn it this way. You probably don't. But, you go 3 to the right, and then you go another 5 to the right, and you get to 8. And it also works the other way around. So you can go 3 plus -5, and that's going to give you -2. Or you can even, go negative twice. And you don't need rules. You just negative direction is to the left, positive direction is to the right, and you basically go first one and then go by one and then go by the other. So that's a simple kind of way of adding the vectors. And then this I did. So this they told me how to do. And this I thought, okay, well, what about multiplication? And so I thought about a multiplication as a scaling. So this little dash number line on the bottom has this gray number 3, and then if you multiply it by 2, and the slider was restricted to integers. So multiplying it by 2 means you scale it by a factor of 2. You make it twice as long. So if you multiply it by 3, you're going to make it 3 times as long. You multiply it by 5, you're going to make it by 4. 3 times 4 is 12. Okay? You're going to make it 4 times as long, right? So far, so good?
Yes. Yeah.
Pretty straightforward. Okay, now we come to the interesting part, which is what happens when you multiply by -1. And we've done this. So this is equivalent to a what? What's the transformation?
A dilation?
The dilation, yes, with scale factor.
Oh, -1 with the dilation, or the center at 0.
Right. And what isometry isn't the important thing. And if we did it by -2, it would do that. Yeah. But let's stick to -1 for a minute. And instead of a dilation with scale factor -1, can we express that transformation in a different way?
Reflection.
A reflection across what line?
Oh, the y-axis.
Yeah. That's one way, and that's good.
Or
what's another? Somebody else. What's another way? That way required us to, to make a y-axis. Is there? Well, forget that. That was a silly thing to say. Is there another, Logan? Is there another transformation that takes the gray one, the gray vector onto the magenta one?
Rotation, yeah.
Rotation by how many degrees?
180 or half turn.
180, right. 180 degrees around.
Oh, 0 or.
Yeah, 0. The origin, yeah. Right? The origin of the number line. Okay. Now, suppose we were to multiply by 2 numbers, right? Then we would first do one scaling, and then we would do another scaling.
Mm-hmm.
Right?
Yeah.
So, for example, if we wanted the square root of 8, or 9, let's make it simple, we wanted the square root of 9, we could first scale by 3 and then scale by another 3. Right? So we want a transformation that when we would repeat it, it gives us the right answer. Right? Now, Logan just said that to multiply by -1, that's the same as a rotation of 180 degrees. So, what transformation applied twice would give us 180 degree rotation?
A quarter turn.
Yeah, quarter turn, that's right. And so that's what gets us out of the number line, and that's what tells us that the square root of -1 is not on the number line, but it's 90 degrees this way. So that's where I is. The square root of -1 is up here. And that's the amazing insight that you need to get to really think about complex numbers. Is we extend the number line, we have to go into another dimension. It's like Flatland and Sphereland and stuff. I don't know if you ever read those. But have you ever read those books?
Yeah.
They're really good. Flatland was written in the late 1800s, and it's about imagining a two-dimensional world. And then a three-dimensional figure it comes to visit, but you can only see the 2 dimensions. So he tries to explain what's going on, and it's really quite good. So I recommend it, and it's available in a video too, I think. But anyway, so that's the insight that tells us that complex numbers are 2-dimensional. They're not 1-dimensional. They're 2-dimensional numbers.
Yeah.
Okay?
Okay.
Walter, I can't see you. Are you with me too?
Yeah, I'm with you.
Okay.
Yeah.
All right. So that's that. And similarly, if we want to get the square root of -2, so we had something like this, and we wanted two, or let's say -4. Make it simple. Then we would have to repeat a transformation twice. And what would the transformation be? Well, yeah, it would be a 90-degree rotation, but it would also be a scaling by 2. So that would take us to, so if we want the square root of -4, it would take us to the imaginary axis, but it would be 2i. And then 2i, and then do that again, rotate 90 degrees, and scale again by 2, and we'd get here. And notice that we could go the other way, and so that's why you get the plus or minus 2i. So, we could rotate 180 this way, we could also rotate 180 this way. So that is a motivation with hindsight. That's not the way complex numbers were discovered at first, but once you kind of see it, that's what forces the second dimension. This transformational point of view is useful that way. And so what I did was I made another one. And this I just did on my own.
Just a question.
Yeah, question.
Could you generalize this method of thinking to quaternions?
I don't know. That's a good question.
I mean, you could rotate various ways in 4 dimensions, quarter turns, and then you get the I, J, and the K. But I'm not sure how you get I and J to equal -K in terms of rotating.
Yeah, I'm not sure either. That's a good thing to think about, Walter. Yeah, I mean, think about that and tell me what you find out.
Okay.
Okay, so I don't want to save my changes on this one. Oh, I don't want to cancel, though. That's silly. Okay, this one. And I don't want to save my changes. There we go. Okay, so here is what I did.
This is exactly.
I have sliders here, and I should have actually. Well, I still have to mess with these and make the colors right and stuff. But the idea in the complex plane should be the same. So if I want to add 4 plus 1i to minus 1 plus 2i, then, and the original vectors are the red one, see the colors coordinate? The red one here and the blue one here. And if I want to add them, why don't I do them the same way? Why don't I add the vectors? And that's why I did head to tail. I took this one, moved it over here, the second vector, and then when we go here plus here, and that gives us here. And so that should, by generalizing the way we added numbers on the number line, we can add numbers on the complex plane. This should be I, 2i. I can't get it to do that. But this should be I, 2i, 3i, etc.
Okay.
All right, so adding, and this is kind of neat because I can move these things around. And I put this up on the class file so you guys can play with this. I'll actually fix it and make it a little better. But there. You know, you can move things around. So this is A plus BI is what the red one is, and C plus DI is what the blue one is. And so you can mess around with these and move them around. And then the magenta is multiplication. And how are we going to multiply? Well, you found that by multiplying what we need to in rectangular form, it's not so easy to see. You know, I mean, yeah, we just do the arithmetic, but there's no visual to that. But if we change it to polar form, which is what I did here, then you can see, you know, these numbers are kind of bizarre, but if you multiply 4.12 by 1.41, you're going to get 5.83. And if you add roughly 14 degrees to 135 degrees, you're going to get 149. So that's the multiplication. So we do scale if we're multiplying by a real number. So it does generalize the previous thing, because if we multiply by a real number has angle 0, and so or 180. But in any case, it doesn't change the direction. It just multiplies by the scaling factor. So it does generalize what we had in the previous sketch for multiplying by a real number.
Okay.
Yeah.
Questions? Any questions?
No.
No.
Okay, so you guys can play with this, and it's interesting to see kind of how to make these things. I learned some stuff about it. I'll post, if you want to look at it, the document that tells you what to do. Tells you at least some of the things to get started, but it's really powerful. And it isn't even made for complex numbers as such. So you can, this text thing has dynamic text as well as static text. So these are dynamic because they're, in other words, by making it be A as an object instead of just typing A, it keeps the value that A has as you move it. It's really kind of cool. Okay, so I wanted to show you that. I'm going to save that. Next, yes. Now what I want to do is stop sharing. So let me go here. I'll stop sharing this screen. Go back here. Stop sharing. And I'm going to change this screen I'm sharing. Let's see. I don't want. Yeah, I want to stop sharing that screen, and I want to share my Blue Jean screen. And stop sharing. Pretty complicated. There we go. Okay, can you see me? All right.
Yes.
So I went out and got some flex straws. I bought these at Safeway. I don't know if you have Safeway, but just what's your big supermarket where you buy food?
We have Tom Thumb, which I think is a Safeway.
Yeah.
You have what? What's it called?
Tom Thumb.
Tom Thumb.
It's the same company
Same
as
idea.
Safeway. Yeah.
All right. And Walter, what do you have in Indiana?
Oh, we have quite a few.
Yeah.
Oh, there's
Name me one or
Kroger.
two.
Oh, there's Kroger. Have you heard of that?
Yeah, Kroger.
What's it called?
Kroger. All right.
Kroger. Yeah, I've heard of
There's
Kroger.
There's Meyer.
Meyer? See, we don't
Yeah.
have that here. I've heard of Kroger.
Yeah,
I haven't heard of Meyer. But okay, so they're different, but you get the idea. Do you have Target?
Yes, we do. We have
Yeah, but
Fiesta.
Target is nationwide.
That's not really a
You can probably
grocery
get
store though.
here. Anyway, so they come in a box like this, the flex straws, and they're not expensive. They're like $1.25 or something for 40 of them. And so I learned how to do this years ago. But you can make models, which is fun. So I started. This is like a cooking show, where you've made part of the ingredients first, right? So you save time. So that's what I did.
Magically bake in 15 minutes.
Exactly. No work required.
So here are two triangles. Here's a third one, and I'll show you how to make them in a minute. And what you do is you tape them. So you need, in order to make these things, you need some flex straws, you need some scissors, and you need some Scotch tape. So
Mr. Douglas.
Scotch tape. And I
Mr.
do.
Douglas.
Yes.
The triangles aren't on screen. Move them to your right.
Oh, I got to be here. Okay.
Yeah.
Now you. Right?
Yeah.
Okay. Sorry about that.
We weren't able to see their glory.
Yeah, thank you for telling. And I used the colors to make each face one color because I thought that was nicer. All right. So you do two pieces of tape per edge.
Okay.
All right. Now, how do you make? So I need another one. I mean, this looks like it's made, but it's not. Whoops! I have to tape this too. Not just one, but two. Take that, and we take this. Okay. Now, how do you make them? Here are 3 blue straws. Yeah, you're right. I gotta really watch here. 3 blue straws. Okay.
Yep.
The way you make them is, you take the short part and you cut a slit from up to the flex.
Okay.
So I'm gonna do that on all 3 straws. So here's one. Here. Here's 2. And here's 3. These aren't going to be perfect because the straws aren't exactly the same. And then the reason you did the cut is you can squeeze it and make it smaller because of the cut. And then you here, I'm going to watch this. And you put the short end into the long end, and you try to push it in till it goes up to the flex.
Okay.
So there's that one. And then the same thing here. Squeeze that down, get it in. I didn't squeeze it enough. To try to get it in all the way to the flex. There. Okay. So now I have this long thing, and then I bend it. I bend it again. And then I do the last short one into the long one. And there's my triangle. So that's how you make the triangles. And now I put it on here. And now I have to do 3 edges, so I need 6 pieces of tape. When we used to make a ton of these when we did these workshops, we would just sort of cut make lots of pieces of tape on the table first, and then just tape them. It's like mass production. And we had a couple of people, several people to do it, so that helped. And it's easy to miss the edges. And I'm doing this for a reason, because we're going to do. There are videos that show some 3D symmetry of these things, but there's no substitute, I think. And you can watch the video later, but there's no substitute for having something in your hands. I do everything? No. Here. Because that's the way you really can see it. A 2D representation isn't the same. Maybe when we have easy holograms for everybody, we won't need this, but for now we do. So here it is. And this is not great because it's too thick. I wish I had a dowel. But we talked about rotational symmetry of this, and you all said it had 3-fold symmetry, because you can go 1, 2, 3, and then it'll match up with itself 3 times in 1 full rotation. That's fine. Mm-hmm. But I claim, and this is what you're not going to see unless you make one of these things, these have more symmetry than you think. So we talked about the planes, and that's fine, but it has more rotational symmetry. There's another axis. There's another axis. Can you imagine where it is?
Is it on one, like the midpoint of one edge to the midpoint of another?
Yes.
Yeah.
Yeah, we hold it like this. Bye. We hold it like this. So the midpoint of one edge to the midpoint of the opposite edge. That's right. I don't know if this is too thick to put through, so I'll just hold my fingers and watch the top. I'm going to make 1 full rotation. Okay. So there's half a turn. It matches once. And half a turn, it matches twice. So, you can kind of see, but making one yourself is really what you want to do when you want to play with it like that. So this has some 2-fold rotational symmetry also, and it has a number of axes like that. So, how many and all that. So think about that. And what I asked you to do is to make one of these, and the homework, of course, is due on the 17th. And make one of these and make a cube. And to make a cube, you need 6 squares. Okay. So you make 6 squares, you put them together, and find more symmetry. There's more symmetry in a cube than you'd think. So try to find all the symmetry. There's a lot of it. Okay, so that was that. Then the last part, and we may not be able to finish, but that's okay. I'll post it. So now I'm going to go back to sharing the Adobe Connect screen. So I'm going to say share screen, and that's the right one. Okay, share entire screen there. Now I'm going to share my screen on Adobe Connect, and here, and here. I don't need that. Why do I do that? What I want is the proper file. So this one is also part of the homework to make this. So I'll just say a word. To make this, you can paste these on 2 sides of a cardboard triangle, but use stiff paper if you can, and make it the same size, because you want to put the triangle over this 1, 2, 3. And if you use stiff paper and then you can flip it over. So you can either label it on both sides or cut these things out and paste them. Either way, but it should be stiff. And then once you do that, we'll be able to do more. Okay, this we don't need. This we do. So I'm going to go to the last part first, and then I'm going to go over the previous stuff. So this document is the history and utility document of complex numbers. And right, 6. Plus, yeah. No, that's not the one I want. Wait, okay, sorry. Let me open the right one. Goes in the class today. Class. E6 class, and I posted stuff. Now I called it plus because I added to it. I want this one that I did this morning. That has 5, early this morning. Okay. Takes a minute to load because it's long. Less than a minute. Okay. I'll make this 200 and go down to number 6. Or not that. There's something more. What the heck? Oh, okay, I see. 5. We get there. 6. Here we go. Okay, so this is what. Can you see this?
Yes.
Yeah.
All right. So I'm assigning. Okay, I thought I changed some things, and I did. This is still not the right one. All right. Anyway, I'll put the right one up. I don't know why I can't get the right one here. Got saved somewhere else. But the idea is that I asked some questions in here, and I put them in red. You can't see on this one, but I put the questions in red, and those are the questions that I really want you to answer. And the reason I did this is because I wanted to show back before, starting at number 2, I asked you folks to fill in the missing steps, and I didn't really get what I was hoping for. So I want to show you, and I'll post this document correctly in the 3-6 homework, what I mean. So what happened was here, for example, this is number 2, where we were proving the cubic formula. And we got this 6th degree equation, but it's a quadratic in u cubed. And then it says, solve for u cubed with a quadratic formula and substitute, I'm sure, and substitute into u cubed plus v cubed equals q to solve for v cubed. So there are missing steps there. So what I was hoping to see was use the quadratic formula. So u cubed equals minus d, so to speak, minus the coefficient of the linear term, so q, plus or minus the square root of q squared minus 4pq, four of these, 4ac. A is 1 and c is this. So, should that be a plus? Yeah, it should be. Okay, I have to fix the sign here. But basically, I wanted to see this kind of thing, and so I put the missing steps. This should be a plus, shouldn't it? Because minus 4ac, this should be a plus. Let's change that while I have it. Okay. And this should be a plus 2. Same reason. Okay. So what happens is some pretty fancy algebra here. You get u cubed is equal to this over 2a. A is 1, and then if you distribute the dividing by 2, you get this, and then dividing by 2 means dividing by 4 inside the square root sign. So that's where you get the q squared over 4, and then dividing by 4 it gets rid of this 4 in the numerator. So that's where you get the p cubed over 27 from. And then since u cubed plus v cubed equals q, to get v cubed we subtract. So what happens is the plus or minus becomes a minus or plus, because q minus q over 2 is q over 2. So you get one of them is plus or minus and the other is minus or plus, but it doesn't matter because we're adding them. So one is plus, one is minus. So when you add them, one is plus, one is minus. And that's how you get x. Those were the missing steps. And I didn't see any of you get that done, I don't think. And so similarly, now here, Ryan, do you understand this now, that you don't have to go back and do the whole thing all over again?
Yes.
Yeah, you just have to substitute minus p for p.
Got
okay.
it. Got it.
That's all. Because, because today we would just rewrite, instead of x cubed equals px plus q, we would write x cubed minus px equals q. And that's the same as x cubed plus px equals q, except the p is replaced by a minus p. So you take the same this is the old one, and you replace p by minus p. And you get this, and that's all there is to it. In the 1300s, they thought it was a whole different problem, and they started again. So that's one example of the usefulness of negative numbers. So we don't have to have 5 million different forms of stuff. You just, it's the same kind of thing. So that's the cubic equation for the cubic formula for a cubic equation of this form, sometimes called a depressed cubic. And then this stuff, which is not so easy, but so I filled in the missing steps for you. We have x cubed equals, we're just trying to solve x cubed equals 15x plus 4. The solution is 4. You can guess at it. It works. 4 works. But when you use this cubic formula, you get this bizarre thing. So there's some motivation to try to play with it. And that's what Cardon, who wrote about this, that's what he did. He said, this stuff doesn't make any sense, but I'm going to do it anyway. That's more or less what he said. I got the information. All the information comes from this book. This book here. It's called The Story of the Square Root of Minus 1. And it's written by Paul Ney.
Yeah.
And it's this thick. and it's really quite interesting. A lot of computation and stuff, but so that's where I got these ideas from. And then, so you get this thing, and where do you go from there? How did he get this? The answer is this: there are missing steps. And the missing steps are, you plug in this formula, you plug cubic formula, you put p equals 15 and q equals 4, because that's what's here. P is 15 and q is 4. So if you put p equals 15 and q is 4, you get this thing, which looks like, oh my God, this is awful, but you don't even need a calculator for it, because this 4 over 2 is 2, and 4 squared over 4 is 4. And then 15 cubed over 27, what some people might do is say, okay, what is 15 cubed, and then use a calculator, whatever. But 27 is 3 cubed. So it's 15 cubed over 3 cubed, which is 15 over 3 cubed, which is the same as 5 cubed, which is 125. You can do that in your head. So it's 4 minus 125, and that's where you get the minus 121. That's where that comes from.
Okay.
So he tried these things, and it didn't work. It was only when he realized that that the two, that the cube root of this bizarre number and the cube root of this bizarre number should be conjugates, because the only difference is a plus here and a minus here. So if that's the only difference, then one of them probably should be a plus b root minus 1, and the other should be a minus b root minus 1. And guessing at the answer was what did it for him, because then he set this equal to this and set this equal to this, and then he cubed both sides and he used the identity, and he said he came up with this. Well, there's some missing steps, and that's what I wanted you to do. So here are the missing steps. If you do what was said, you get 2 plus and 121. Square root of negative 121 is the square root of 121 times the square root of minus 1. And that kind of thing works except when they're both negative. So square root of 121 is 11. So it's 2 plus 11 times the square root of minus 1. And when you cube it, you get this whole bizarre thing. But if you rewrite it, what happened? What did I do? Sorry. I hit something that I shouldn't hit. There we go. When you rewrite it, this is the real part, and this is the imaginary part. And the real part is 2, and the imaginary part is 11. So that's where he gets these equations from, just by factoring out an A here and factoring out a B here. And then, how do you find a solution? Well, he assumed, okay, suppose they're integers. Let's start with the easy case. I mean, that kind of thing is really useful. And 2 and 11 are both prime. So one of these has to be 1. So you might try A equals 1 first, and that turns out not to work. But then suppose this one is 1. Well, how can we get 1? Well, gee, if here's a 3, and if this were 4, then 4 minus 3 would be 1. So that looks good, right? So if A is 2 and B is 1, and that turns out to work. So probably by trial and error, he did that. And then, so the last thing is, this bizarre cube root is 2 plus the square root of minus 1, and this one is 2 minus the square root of minus 1. And when you add them together, you actually get the solution, which is 4. So that was the original motivation of saying, these things look stupid, but I want to play with them anyway because they may turn out to be useful. But it took, this kind of stuff it took 500 years before these numbers were accepted. And you know what? Actually turned the corner? What made people actually accept them? Take a guess. I'll tell you because we're out of time. What made them be accepted is somebody with stature said, these are good, you should use them. And the person with stature was Gauss in the 1800s.
Oh, Gauss.
That was it. Before that, people would argue back and forth, we shouldn't use these things. So the history is interesting, at least for me. So it's 10 o'clock. Enjoy your vacation. Except for Walter, but enjoy your time off for the course anyway. And
I have a question.
Yeah, what's your question?
So, during my spring break, which week are we having classes?
We're gonna meet the second week. Your spring
I'm
break,
gonna be
not the first.
I'm gonna
week,
be
okay?
overseas. My mom recently booked me tickets to China for the entire spring break.
Okay,
This
so
was
you
like-
can't come.
Yeah.
All right.
Are we still having class then?
I don't know. Let me think about it. I'll let you know.
Because if we do, can these not include on my attendance record because
Yeah, no, I understand. I understand.
yeah.
So, let me think about that. I'll talk to Miss Sobe and find out what I can do.
All right. Okay.
But that makes
Okay.
sense. Okay, thanks for telling me.
Yeah.
All right, take care.
Yep. Bye.
All right.